If you want to get these questions right, to have the right sign for your answer, which is important, because a negative sign means energy is released, a positive sign means energy absorbed. In the industry, if you got that mixed up, you could have a really dangerous situation. If you think energy is going to be absorbed, and so you heat the system up to get it going, but energy is actually released, plus you're heating it, that's going to be way too much energy building up in the surroundings, and it could cause an explosion or something like that. So conceptually, this one's a lot easier to remember. The other one you just kind of have to memorize, but this formula makes sense because it revolves around what's happening with the bonds. And we know already from many times of repetition that when bonds are breaking, energy must be absorbed. So from the system's point of view, when it's absorbing energy, that's always going to be a positive. So these are bonds that are breaking. I have to break the bonds of the reactants to get the electrons rearranged. Then when the products form, and I'm forming bonds, that is a negative from the point of view of the system because it's always releasing energy when bonds are formed. So we don't really have to memorize this one as long as we know when to apply it. And we apply it if we're given bond dissociation energies or bond enthalpies, because those represent the quantities of energy associated with breaking individual bonds. So a hydrogen-hydrogen bond, if I were to break that and separate the hydrogens so they're not sharing the electrons anymore, that requires a specific amount of energy. There's a specific amount of energy required to dissociate or break that bond. And from the system's point of view, that's always a positive. So bond dissociation energies are always given as positive quantities. I have to recognize, though, if my reaction is forming that bond, then that's going to be negative because it's releasing the energy. So here's a table in your textbook that shows a variety of bond dissociation energies for lots of bonds. So let's just look at one, for example, carbon-carbon maybe. Not every carbon-carbon single bond requires exactly 347 kilojoules to break per mole of bond. That's the average, right? So when you use these numbers, you're never going to get the exactly correct answer because some bonds take a little bit more energy to break. Some carbon-carbon bonds are a little different than others. But they should be pretty accurate because if you have certain bonds that you have to break, like in this example, 2 hydrogens are breaking, 2 chlorines are breaking. To break the hydrogens, it should absorb 436.4 kilojoules per mole of hydrogen-hydrogen bonds that are breaking. To break the chlorines, it should absorb 242.7 kilojoules per mole of that. So if I were to break a mole of each, that would, the sum energy associated with that would be absorbed, and so that's a positive number. So when they're not forming their bonds, it's very unstable, it's higher in potential energy, so I have to put that energy in to break the bonds. And then if the new bonds, since I'm forming 2 HCl bonds, each one of those is going to release 431.9, and so the quantity released, in this case, is greater. So the difference between those two quantities is the net change. Right? So I take all the energies absorbed, subtract from that all the energies released, and I can figure out the net quantity of energy absorbed or released. This particular reaction will be released because the new bonds that are forming are more stable than the old bonds that I started with. Another example here. So you can kind of see how it's helpful to have a Lewis structure because you have to see all the individual bonds breaking and forming. So in this case, I've got NH3, which has 3 NH bonds. But in the balanced reaction, that's 2 NH3s. So if I've got 2 of those, that's a total of 6 NH bonds. So if each NH bond is 393, that's going to be 6 moles of NH bond multiplied by 393 kilojoules per mole of NH bond. So that's going to be, actually this is 6 moles of NH bond per mole of reaction. So that's going to contribute 6 times 393, that's the quantity of kilojoules that has to be absorbed every time I do a mole of the reaction, because 1 mole of the reaction requires 2 moles of NH3, and that's 6 moles of NH bonds. So it's really helpful to have a Lewis structure here to see how many of the bonds are actually breaking. So those all have to break. So that's going to give me the sum positive energy that's absorbed. Then on the product side, I form one nitrogen-nitrogen triple bond, and how do I know it's going to be a triple bond? Well, I've got to draw the Lewis structure and make sure that I make it stable with the right number of valence electrons, and a triple bond is necessary to do that. And I'm also going to have 3 of these HH bonds. So to release energy when the bonds are formed, I'm going to be releasing the nitrogen-nitrogen triple bond. And since only one of those, that's per mole of reaction. For the hydrogen, I've got 3 moles of hydrogen bonds per mole of reaction, and each one of those is going to be releasing 436.4 kilojoules per mole of hydrogen bond. So these are all the energies being released. Add that all up, subtract it from the total energy being absorbed, and in this case the net happens to be positive. So overall, this is an endothermic reaction because it's absorbing more energy from the surroundings to break the bonds initially than it is releasing when the new bonds form. Questions about that? So here's another example. Here I'm doing a combustion reaction. I want to know what delta H is for the reaction. I can use heats of formations. I could use Hess's law if I had a number of other reactions I could add together to produce that reaction. Or if I have all the energies associated with breaking all the individual bonds, I can use those energies to determine the delta H for the reaction as well. So in this case, I have to break 4 CH bonds. So 4 CH bonds, 4 moles of CH bonds per mole of reaction, because there's only one of those in the reaction. And each one of those is 414, so that's absorbed. 414 kilojoules per mole of CH bond. So that has to be absorbed. That's going to be positive. I'm going to add to that the energy absorbed to break these bonds. And I've got 2 of them, 2 moles of O2 bonds per mole of reaction. And those take 498.7 kilojoules per mole of OO bond. So that's going to be multiplied by 2. That's going to be all the energy that's absorbed. That's all the bonds I have to break. Then I'm going to release energy. I'm going to release the sum of all the energies associated with the bonds on the product side. So I've got to form 2 CO2 bonds. So 2 moles of CO per mole of reaction. And those are 799. 799 kilojoules per mole of CO, double bond. And then I've also going to form 4 OH bonds. So I'm not counting up the number of molecules, I'm counting up the number of bonds here because the energies I have are for individual bonds. So 4 moles of OH bond per mole of reaction. And I have 460 kilojoules, should be a decimal here, 460 kilojoules per mole of OH bond. So now that cancels. So again, all of my units have to be the same if I'm going to add or subtract numbers. So that's why I have to cancel all the moles of bond and just have everything in kilojoules per mole of reaction. So then I would just plug that all into my calculator I would, I'm not going to do it, just save a little time here, but I would add all this together, multiply 2 times 498.7, multiply 4 times 414, add that together. Then I would subtract the sum of the 2 times the 799 and the 4 times the 460, and then I would get my answer, and it would be negative in this case because the sum in this parentheses is larger than the other one, which means that it's exothermic because I'm releasing energy from the system to the surrounding.